Good morning, honorable examiners and guests. We are Calvin, Fadel, and Arif. Today, we are representing our research titled Pattern Stability in Post-Crisis Small Medium Enterprise Lending, a Time-Split Classification Framework. So in the next 15 minutes, we will demonstrate a critical flaw in how financial data scientists currently evaluate credit risk, and we will propose a framework designed to fix it. Our presentation is structured into 5 key sections, and I will begin by introducing the phenomenon of concept drift and the literature gap in current validation methods. And my partner Fadel will then detail our methodology and modeling architecture. And finally, Arif will present our empirical results, feature shift analysis, and our core conclusions. So let's start with the core problem. Small and medium enterprises, or SMEs, drive economic growth. However, because they possess low cash reserve, they are highly vulnerable to macroeconomic shocks. During financial crisis, we see a massive spike in defaults, but the real danger is what happened after the crisis. Borrower risk profile are non-stationary. A business that fits a low-risk profile during a stable economic period can rapidly exhibit a high-risk profile during a post-crisis recovery. This phenomenon is known as concept drift. The problem we face today is that static credit scoring model fail to capture these nonlinear economic shifts. When model fails, financial institutions are destabilized. And our goal is to evaluate the stability of SME's loan pattern using a continuous, chronologically robust assessment framework. And this brings us to a major flaw in current literature, the look-ahead bias. Currently, the industry heavily relies on a random k-fold cross validation, and this approach randomly shuffles data, completely ignoring strict chronological timelines by mixing historical data with future data during training. And these models inadvertently cheat. They learn from future economic state before they are supposed to artificially inflates their performance metrics, rendering their high scores absolutely useless for a real-world applications. And banks cannot predict the future using data from the future. And to solve this recent advancement, propose out-of-time testing, or OOT, as the gold standard. OOT enforces a strict temporal boundary between training and testing data, coupled with powerful ensemble techniques like light GBM. OOT evaluation provides a realistic assessment of a model's true robustness against distribution shift. And I will hand it over to my partner Fadel to explain how we implemented this methodology.
Okay, thank you, Calvin. And to ensure our model could handle real-world economic shock, we utilized the U.S. Small Business Administration dataset. This dataset covers the period from 1987 to 2014, capturing both eras of extreme economic stability and the severe 2008 financial crisis. And in our pre-processing phase, we rectified missing values and encoded categorical variables, such as business types and location, into precise numerical formats. Crucially, financial data is inherently unbalanced. There are always more successful loans than defaults. And to fix this, we applied the synthetic minority oversampling technique, or SMOTH. However, to prevent data leakage, we applied SMOTH exclusively on the training data. And this leads directly into our core methodology, the time-split framework. As Calvin mentioned, we reject random data shuffling. Instead, we institute a strict chronological split. We train our model strictly on pre-2009 data. By applying SMOTH only to this historical training set, we resolve class imbalance without leaking future information. Then, we conduct our predictive modeling. We evaluate our models on an entirely unseen post-2010 test set. This creates a hard wall of time, mimicking exactly how a bank would deploy an AI model in reality. And for our modeling architecture, we benchmark three specific approaches. First, logistic regression, which serves our standard parametric baseline. It assumes linear relationship and generally performs poorly on highly complex, changing post-crisis data. And second, we use random forest as our ensemble baseline. It uses a bagging strategy with multiple decision trees to handle non-linearities. But without chronological tracking, it's still vulnerable. And finally, our proposed champion model, the light gradient boosting machine, or light GBM. Light GBM utilizes leafwise growth. It is highly optimized for speed and specifically designed to capture complicated nonlinear patterns in unbalanced financial data. And to present the empirical results of this architecture under our time split framework, yeah, I will pass the presentation to Arif.
Okay, thank you, Fadel. Before looking at model accuracy, we must first look at the empirical evidence of concept drift within the data itself. Okay, so in our pre-crisis training set, which contained over 850,000 observations, the default rate was 17.52%. However, in our post-crisis unseen test set, the default rate dropped sharply to just 8.74%. This is an 8.78% point decrease. This massive shift signifies that banks become much stricter and the profile of an approved borrower fundamentally changed post-crisis. Okay, this confirms exactly why out-of-time validation is absolutely necessary. Okay, model validation and performance. So, how did our models perform under these shifting conditions? So, like GBM proved highly robust, achieving an out-of-time AUC of 0.9649, and it significantly outperformed random forest, which only score about 0.9232. Okay, and logistic regression, which failed to adapt to the nonlinear shape, scoring only 0.6315. That is extremely low between our top three models. Okay, but the most critical takeaway is the inflation metric. When we test the like GBM using the flow random forest method, the score was artificially inflated by 1.16 percentage points. This inflation highlights the extreme danger of look how ahead bias. In the financial sector, overestimating a model's accuracy by over 1% due to random validation can lead to billions in miscalculated risks. So this is very, very, very dangerous. Okay, now is pattern stability and future shift. Beyond the accuracy, we analyze what specifically changed in the borrower profiles. Our experiments rank correlation yield a score of 0.9393, indicating that core risk pattern remain generally stable. And the loan duration or term and borrower location remain the number one and number two prediction across both lines. However, specific banking priorities shifted. Post-crisis, the total employee headcount dropped significantly in importance, falling from rank 3 to rank 6. Conversely, the total disbursed amount and project job creation gained crucial predictive weight, and banks shift their focus from passive company size to the actual economic impact and strictly control loan size. Okay, so the conclusion, the path forward, this brings us to our final conclusion. First, regarding chronological validation, developing reliable SME loan default prediction system strictly requires chronological validation to accurately reflect real-world financial pipelines. And now, second, regarding the random testing flow, standard random testing allows models to cheat from look-ahead bias, dangerously overestimating performance metric in dynamic economies. Finally, like GBM robustness by enforcing a strict time split framework. We have proven that like GBM can accurately and safely predict involving credit risk without falling victim to concept drift. Okay, now it's the end of our presentation. That concludes our present. Thank you very much for your time and attention throughout this recording. The next time we can take together are now displayed on the screen, and we look forward to our future collaboration. Thank you and have a great day. Thank you very much.